Okay, welcome everyone. Today we are very happy to have Ivan Danilenko from UC Berkeley, who is going to tell us about quantum cohomology and slices of the affine Grassmannian. Please go ahead.
Yeah, thank you for allowing me to give a talk. I gave a similar talk like almost a year and a half ago on the same seminar. So feel free to ask me to give some more details on or skip some particular parts. Yeah, I still think that some background should be reminded, but since whiteboard style is more flexible than slides, I can actually spend more time on the parts you find more interesting, okay? And questions are always welcome. So this talk is based on my PhD thesis, but definitely many structures which are involved there were discovered long ago. So what structures do we consider here? So that would be answer for the first question, for the first part of the title. What do we mean here by quantum cohomology? So surely for any topological space, we can consider just cohomology, right? What else can we do? If we have some sort of torus section, we can upgrade it into equivariant cohomology. I'll drop the notation of the coefficients because I always assume that I'm working over a field. So these are equivariant, equivariant cohomology. Right, and this is algebra with respect to the cup product. Okay, and now I will deform the cup product to get something which is called quantum cohomologies. So as a space, it is as a space that's the equivariant cohomology times some power series in formal variable q. And here so we deform the cup product to the new multiplication, which is called star, the quantum multiplication, and it's defined by the following thing. So instead of saying what the product is, I will say how it pairs with any other element. So it will behave like the ordinary cup product plus some corrections which capture the curve counts in my space X, and it will be 3-point Gromov-Witten invariance, and some formal parameter which keeps track of the degree of my curves. So these things are 3-point Gromov-Witten invariance, right? And they count curves of degree d with some conditions implied by A, B, and C. Okay, so that's quantum cohomology. And to be honest, I'm not interested in quantum cohomology itself, but in I'm more interested in a problem which is formulated in terms of quantum cohomology. So if I look at the space, which is quantum cohomology, I can think about this thing as coordinates on some base of a fibration. And this would be fibers, right? And then I can make the following object, which is called quantum connection or Dubrovin connection, which is the following thing. It's an operator which is partial derivative with respect to lambda plus the quantum multiplication by lambda. Here lambda is some class in second cohomology, so it's naturally a coordinate on this base. Okay. This connection is known to be flat. Okay. Actually, that's not exactly this coordinates, because my degrees, they live not in equivariant homology, they live in non-equivariant one. But if I take just purely some purely constants instead of my second cohomology, this is not interesting. So we will focus on transversal directions. Okay, I can still write this for constants, but that then would just mean that just multiplication in this case would be act on everything in the same way, and in this direction there is nothing interesting actually. Okay, and we want to express this quantum connection in terms of more well-known connections, flat connections. Okay, so surely the answer would depend on what space you consider, but we will do it for a special family of X. Okay. So another way you may think about this that we try to understand quantum multiplication by understanding how to multiply by the simplest possible classes. Okay. Okay, let me start not with the spaces I want to consider, but with the answer. Okay, so we will use when I will finally reach to the point where I define the spaces, it will be the resolution of a slice in the affine Grassmannian. We'll come to there later. Okay, and I know how to do it in ADE types. I know good identification in AD types. Okay. So let's
And
start.
how about outside AD? Have you, will you tell us a little bit about what happens outside of AD? There should be a story there as well, but.
Yeah. So, just the problem is that I don't know a good name for what I get there. That's the only thing. When we will discuss the answer, I can actually show you what happens in B. I'll explain what happens in BC, for example.
Excellent.
Okay, good. So let's start with some representation theory. So the answer will be formulated in terms of representation theory. So let's start with G check be a complex connected reductive group. So for example, it could be SLN, PSLN, some groups like this. Okay. So, and let's take several representations of it, different representations, complex representations. So now let's introduce some notation. So if we have some operator in the Lie algebra, we'll write xi for x acting on ith position in the tensor product. And similarly, for if I have something in tensor product of two guys, we can act on two positions now. So I'll have two indices. All right. Yij for the operator acting by the first component of y on ith place, the second component.
I have a question. These things are also Coulomb branches of 3D gauge theories. And
the space, yeah. Mm-hmm.
And the Coulomb branch picture gives you sort of a very nice way of thinking about well, there are many different ways of thinking about a space. But the one that comes from the Coulomb branch or monopole moduli spaces gives sort of a very nice representation in terms of basically essentially hyperplane arrangements. Or I wonder whether that view was like useful for you in this.
I'm not sure what you mean by hyperplane arrangements here.
So essentially, in all AD cases, the data of what the geometry is, everything you need to know about it, is like a symmetric product of points on a line, where at some special point you have your representations inserted, and then you know, and you have a symmetric product of whatever is like the dimension of your space. So it's almost like a hypertoric, it's like a hyperplane arrangement kind of picture of it, right? To me, it was a very powerful way of thinking about the geometry, because otherwise, thinking of it complex algebraically, it's a little bit hard to swallow. At first, it's useful, but it's the different views are complementary and useful for different things.
Yeah, but actually, maybe I misunderstand what intuition you have about it, but this transformations and like it's more or less Hecke transformations, as far as I understand what you mean, right?
It's exactly the Hecke transformations. That's right.
So the same description works for any type. So you just stack your monopoles there. So like, but if you stack them at the same point, you have some possible like cancellations in charge, if you want to think about it in this way. So I don't see any difference between AD types and everything else.
Oh, no. The question is, if we, okay, eventually we would like this quantum differential equation that you're talking about to be some nice differential equation from mathematical physics, like Knizhnik-Zamolodchikov equation.
Mm-hmm.
And then the question is, what is the right space for that to be the answer? So in non-Laplace cases, but maybe we shouldn't get too far ahead of the story. My question was just general. I didn't mean to
yeah, I'm not sure what's the correct version to make actually Knizhnik-Zamolodchikov outside of type AD. I just try to do it for candidate spaces, and it just turns out not to be this one. So maybe there is a corrected version. I just don't know it.
There definitely is. We can talk about it.
Yeah, sure. Okay, so there was a question in chat. What do I mean by X acting on I position? So let me just make it more explicit. So if I act on something like this, then it would be just this. Okay, and similar for the for Y's. Okay, yeah, that's pretty standard notation when people describe Knizhnik-Zamolodchikov connection. One more piece which I need is the Casimir operator. So because we have the symmetric invariant pairing, that actually gives us a dual operator. Here I don't write duals because by the same pairing we can identify the algebra in the dual space. And the image of one is called the Casimir operator. Sometimes you call by the Casimir operator its image in the universal envelope in the central element, but let me keep it split. So explicitly, you can write it as omega equals summation over xi's plus summation over roots it's like this, where we take dual bases in the Cartan subalgebra. Right, and here I'm a little bit sloppy about what elements I take here, but these are elements in alpha eigenspace, in root subspaces. With root alpha. So actually, because I gave the description in terms of being dual to the invariant pairing, you can actually get some normalization of these guys by applying this criterion. Okay, so I'm just defining what their eigenvalue is. I'm not saying what actually they are, but you can reconstruct it if you want to. And we'll need half Casimir operators. So I take half of the Cartan part. And then for the off Cartan part, I will take only some roots, only positive roots with respect to C. I'll say in a minute what it means. So here C is a Weil chamber. And the restriction of a root on a Weil chamber is positive means the same as alpha is positive with respect to this chamber C. Okay, so usually people take C to be dominant and anti-dominant. But let me just keep this freedom here. Okay. So now we can write the answer we want to get. It's the trigonometric Knizhnik-Zamolodchikov. Connection. It's just a collection of operators of the following form.
Can I ask you something?
Yeah, sure.
So, I mean, the Weil group acts on the root space. So it makes little sense to me that there's something God-given about a chamber. What I could see is the following: to say, once you choose a torus action on your space, that then that torus action picks a preferred chamber, such that which has some positivity property with respect to that torus action. Having made a choice of torus action, then there's a chamber you want to choose.
Well, when we make torus action, we can have different chambers of it.
I know, but so, it's for me, a choice of a torus action is just a choice of
one character.
Yeah, that's right. In the Cartan, and then in fact, I can think of it as being like roots G real numbers. Okay.
Yes, but for me, it gives some attraction and repelling of.
Exactly. No, that choice is important. But once you made that choice, then you choose a chamber such that, say, this is like all the like the inner products are all positive or something like that.
Yes, sure, but
right, okay.
And the point is that in my description there will be some choice of bases which depends on this C. Because of this attraction and repel in the relation, I'll have different bases actually.
Yeah, so it's really a choice of bases that depends on a choice of a torus action.
Right. So well, I think I just phrase it a little bit different. I think that torus action is given on the whole torus, And then choosing of one parametric subgroup there is the same as choosing the Weil chamber here. Because actually, if I don't cross the wall, all characters for me, all co-characters for me are the same. All one parametric subgroups are the same. Okay?
Sure.
So that is some extra choice, which we will see in geometric side as well, when we will choose the basis. Okay? Just for usual trigonometric Knizhnik-Zamolodchikov, people just pick dominant and anti-dominant chamber, but we could take it like this. Oh, yeah, I didn't finish writing the formula, so my half Casimirs acts on I and J. Okay, and here, these HIs are the elements in Cartan. You can definitely get rid of them by some redefinition of things, and you can get rid of H bar, but let me just keep them in this case. Let me keep them explicit. Okay. And we'll act by these operators on a product of highest weight representation. So these are just simple reps with highest weight λ1. We'll act on this, and because we have these, we'll actually need to tensor it with rational functions in Z. And we have this explicit parameter H here. Okay. And because of the choice of our operators here, they don't mix different Cartan gradings. So we could actually restrict here to weight space mu. So mu weight space. Okay. So that will be our thing. And later we'll see that we have all these parameters in the family of spaces we consider. So let me now say that in quantum cohomology, I actually have power series. So to compare with power series, in quantum cohomology, let's expand in the region where the first Z is considered to be much smaller than Z2. So, okay. So the bigger the number is, the bigger the variable is. So then I can write that this operator is actually let me first write things which become constants, which don't depend on H, which don't depend on Z's. That will be so here it's GI. Okay, and then what is left here would be smaller things in terms of this order. And here we'll have not half Casimirs, we'll have the usual Casimirs. And here I claim that this is the contribution from classical multiplication. And the second thing will come from corrections in the purely quantum part. Okay. So if we look at this now it's more or less clear how this extra term, not the derivative is clear, how the this gadget should be the quantum multiplication by something. Okay. And now the theorem is that under identification, first of all, we need to identify the spaces. With equivariant cohomology of some space I'll consider later. You see they have similar data. And one part of here is choice of basis. And actually you will see that then we will have that the standard basis here corresponds to some special basis which are called stable envelopes. And moreover, there is C in the half Casimir element here, and it actually corresponds to C in this choice of basis. Okay, well, that's so far only on the level of spaces. And then we need to understand how to identify these with EIs, with this Q to some power. So ZI should be more or less Q to some. These are some homology classes. And then saying that I expand it in the region like this, it's the same as saying that EI minus EJ is effective. So it corresponds to some curve. It's not just a formal combination of negative coefficients, right? And then finally, here I have I, and it should correspond to some different parameters, lambda I, and lambda I is first Chern class, equivariant Chern class of some line bundles, some T equivariant line bundle. And there it would be exactly the same number of them. Okay, so under this identification, we'll have that Knizhnik-Zamolodchikov is the same as quantum connection. Maybe let me say that this H actually might look annoying, but it appears for the line bundles I take. Like all classic, you can change the the equivariant structure of the line bundle, and then you can correct this H. But for the most natural choice of the equivariant structure, you'll have this H there, just there.
Sorry.
Okay. So let's discuss what the spaces are then. So we more or less know what we're trying to show for this quantum connections. So let's start. So all the way before I used Langland's dual notation, because now I will use just G. And every time I had weight on one side, I'll have actually co-weight on the other side, and vice versa. There is Langland's duality between the objects involved. So let G be a complex, connected, reductive group. And let me take the following two rings, two different power series. Oh, I usually call this. So then spec of O is a formal disk. And spec of K is actually a formal puncture disk. So if you can think about this as it happens in a curve, but it happens locally around the origin, whatever I'll write later. And said theoretically, the Affine Grassmannian is just the quotient of G's, where instead of usual scalars, I will take, instead of usual scalar C, I take this expressions in terms of power series. I just base change them. Okay, but as Mina said, there is a formulation, a moduli space formulation. So Grassmannian G parameterizes all principal bundles and sections. So let me write it like this. P is a G principal bundle on non-punctured disk, and phi is a section is as a morphism of P. Sorry, something is wrong. Of P restricted to the punctured disk with the trivial G bundle, G principal bundle. And then about this, you can think as monopoles at one point. So this is some object which parameterizes all configurations of monopoles which can exist at the point. Okay, which are governed by this group G. So if your group is abelian, there is actually nothing, not much information. You'll just have what charge I have at this point. If G is non-abelian, this is more complicated, and with the same charge, I can have different monopoles. Okay. This Grassmannian G is actually in projective scheme. So it has filtration by projective spaces. So it's reasonable space. And actually there is an and have as an ample line bundle of one which generates the Picard group. Okay. So there is one line bundle which, and all other line bundles there are actually powers of it. The same happens for the projective spaces, right? So it's a very special condition. Okay, and we'll see later. Then I will need this to construct my line bundles E. Okay, now we so from now on we'll fix G, so we omit it from notation. We just keep it in mind that it is there, and everything depends on it. Okay, and now let's consider what actions on the Grassmannian we have. So first of all, I know that it's given by this quotient, right? And I took the quotient from just one side. So from the other side, I can still act by this big group, right? And inside here, I actually have G of O, just if I don't allow poles. Inside of this, I can have just constant things. And inside of this, I have maximal torus. Okay, that's one type of actions. And the second type is that I can actually act on the Grassmannian by scaling Z, which is the disk. So if I scale my coordinate, actually that will be some action. Okay, and for some reasons, I'll write it with subscript H. Would be H, which will be associated with the section later. Okay, so these are the natural actions. Unfortunately, G of K, the highermost, doesn't commute with this one, right? Because scaling of the loop will actually, if I conjugate element in G of K by this, I'll get a different element. But starting at this level, when I have no Z dependence, it starts to commute. Okay, so we'll need this action on Grassmannian. So that's a torus action, and I wrote here just direct product, not skew product, because not semi-direct product, because they commute, right? Okay. So this will be my torus with respect to which I take equivariant cohomology. Okay. When we work with equivariant cohomology, because we quite often rely on localization computations, it's good to know what fixed points are. And the fixed points are described as following. So if we take a co-character, a co-character of A, then we can make an element of GK by just taking the composition. I take the punctured disk. It naturally sits inside of this thing, and this I can send by lambda to A, which sits on G. And maps from spec K to G are by definition G of K, right? We call it Z to the power lambda. In some sense, they behave like powers. If you, for example, take type A, then these things will be just diagonal matrices with, and on the diagonal, you'll have Z to some powers. Okay, so in type A, that's very easy to explain why the notation is like this. And then this gives after I take the equivalence class, it gives me an element in the Grassmannian. Okay. These points are T-fixed because first of all, they are A-fixed because A commutes with A. Then I'll just see that if I try to multiply from the left, I can just transfer it through Z to the alpha, Z to the lambda, and it will be killed by G of O. But also when I try to scale the loop, I'll also get some contribution by the T, which I can move to the right, and then get killed by G of O. So it's also fixed by this. Okay. And then one can show that actually T fixed points in the Grassmannian are the same as A fixed points, and they are just all these Z's. All these Z's for different co-characters. So we have very explicit description for all fixed points in the Grassmannian. Okay. The spaces we will consider are not quite these ones. They are actually associated to some cell structure in Grassmannian. And it's given by the following. So I can write, I can denote by this space GO orbit of my preferred fixed point. Okay. And this is actually as a space. This is a vector bundle over G mod P for some P, which I can read from this lambda. Okay. So one can show that this can actually the Grassmannian is actually just decomposed into these orbits. These are all GO orbits. Okay. This is similar to Brouillard cells in the non-affine Grassmannian, the flag variety non-affine, or usual Grassmannians are more like partial flag varieties. So also partial flag varieties have this form. That's just explicit affine generalization of the previous case. Okay, and I wrote dominant here because actually if I change the character by while group, that will give me the same orbit. So I just want to count them once. Okay, and it's also known that we know how these cells are attached to each other. If I take the closure of one cell, then it's just disjoint union of summation over all dominant co-characters which are smaller than lambda, which are not greater than lambda with respect to Brouillard order. Okay.
And you can picture in some way, right? Like which fixed points are close to which ones. Like somehow it gives you some kind of crystalline structure on this Grassmannian, right? The set of fixed points.
So if I take this is so if I take Grassmannian of lambda like this, so as I said that that's some G mod P and some vector bundle over it, right? But then this direction ends somewhere on the Grassmannian, let's say lambda minus alpha, where alpha is some root. So that's how they're attached. So this like things which, if I look only at one GO orbit, they are just vector bundles which go to infinity. Then actually, if I look at the whole Grassmannian, they somehow end on smaller things, and they end somehow singularly. So that would be the whole point later, that this attachment is not that simple, and it's of independent interest. Okay, maybe one more thing to say about this structure as a vector bundle would be that actually this thing scales the fibers. So the fixed locus is exactly the zero section. So I can contract everything to the zero section in each orbit. Okay. Okay, and one more thing that this Grassmannian lambda is actually the smooth part. So from the description of flag variety and some bundle over it, we know that it's smooth, but it turns out that it's, if I remove all singular points, that would be just this without closure. So actually the condition for this to be smooth is equivalent to saying that the closure is the same as this itself. But then because
should be overline.
Sorry?
Oh, sorry. That's okay. Sorry.
Yeah. Okay. Thanks. Okay.
So when lambda is a minuscule weight.
Yeah, that's what I'm trying to write.
Okay,
this is the same as lambda is minuscule.
Yeah. So it should be overline, like right. So lambda bar is smooth.
Oh yeah,
yes.
Right. Yeah, they're always smooth. Yeah, thanks.
Yeah.
But if we're saying about like this closed things, they're smooth if and only if lambda is minuscule. Equivalently, that would be that I don't have these fibers. They'll be just like points. So I don't need to end anywhere, and they will be actually projective. They would be just the partial flag varieties. Okay. So yeah, this would be the this smoothness would be what will allow us to construct some smooth resolution in a second. Okay. So as I said, the way how they attach is not trivial, and moreover, it's something singular. And we can look at the following thing. So I have, let's say, Grassmannian mu, and I have a bigger one, Grassmannian lambda. So here I think that mu is less than lambda, or both dominant. So then I can think that somehow in the closure of the big thing, I have the small thing. And then to see how it's attached, I should consider one point. For example, all points here are equivalent, so I'll just take the easiest one. And I'll see what happens in transversal direction. So technically, because these orbits were given by G of O, and that's like slightly bigger than a half of GK, now I'll take what's left in GK and try to act by it to get some transversal thing. So this space is denoted by this. And this is intersection of the closure of Grassmannian lambda with something which is infinite transversal thing. Okay. So this would be the picture, the transversal picture, how a bigger cell is attached to a small cell. Okay. So so we're interested in these things mostly. The things you need to know about these guys is that, first of all, they're T-invariant. So actually, all the T action I had before I can use here. That's great. Second of all, the fixed points, the T fixed points again are the same as A fixed points. And here is just one point, this mu. And third of all, we have that the loop scale in action, because it scales the fibers, and most of these things lives in fibers, but like over other guys, but still they somehow move. We get that this contracts this to the only fixed point. So that's some singular thing, and here we have an action which contracts everything to the only fixed point. That's how I think about this. And surely the biggest singularity actually sits at the point mu. So that's why I drew it like conic thing. And also this is, well, it's normal affine. Maybe that's not the most important, but what's important is that it's Poisson variety. So it's singular, so it's not symplectic variety, but it's a close relative.
Wait. So say this again. You're saying that that is.
Sorry, you muted yourself.
What's the fixed locus of the H bar action?
It's the only point. It's only one point.
I don't think so. I don't think so. I mean, take an example. Right. Take say T star P1, right?
Yeah, but
the fixed locus
that's
the whole is a P1, right?
That's not
Actually,
it's not.
Sorry, it's not. It's not. Sorry, it's not just P1. It's bigger than P1. It's P1 plus sort of 2 half disks attached.
I'm considering affine spaces so far. That would be affinization of P1, which contracts the whole zero section.
I think it's easy if you think about it in terms of monopole moduli spaces, right? So this thing is a moduli space of moduli space of monopoles on R3, where you broke up the R3 into R times R2, R times C. And then the C star action, this H bar action, just rotates the copy of C. So once you fix that, what you're left with is moduli space of monopoles that sit at a fixed locus, which are just these particles that move back and forth in a line. So the fixed locus is much bigger. It's not a point.
So far, I'm considering Hecke modification at only 1 point. But it can be big. It's lambda. Lambda is not minuscule.
Even if it's so, you can make it singular. You can make it very, very singular, but it's still not a point. I mean, I can the dimension of the fixed locus is still something like the number of roots you have to lower to go from lambda to mu. That's
a dimension of the affine space. So that's the Poisson variety of 2 rho bar lambda minus mu. That's a dimension of the affine space. But there's only one fixed point. So what are you're trying to think is about is the resolution. So for example, if I have P1 and then it projects to the nil cone.
Maybe we're making a different, thinking about a different thing. The locus that's really completely invariant is smaller. I guess maybe that's what you want to say.
Yeah, but it will be in my picture, it would be pre-image of this the only fixed point. So so far I'm considering singular affine Poisson things. So yes.
Maybe you also can make a comment that this GR mu with lower index is a repellent to 1 point Z mu with respect to the loop rotation action. Yes.
That's what I'm trying to say.
So actually, yeah, this by definition, you have one fixed point.
So just I think our misunderstanding with Mina is that Mina tries to think about the resolved case when I try to stack the monopole by minuscule monopoles with minuscule charges. And that would be a resolution and it would be smooth. But so far, I collapsed them all and forgot how I stack them. That gives me something highly singular. So in T star P1 picture, I have that.
I think the confusion is terminology. So that's I think we can move on. It's not the thing that's interesting to me is this locus where all the monopoles on a real line, and that they'll be moving on a line whether or not the space is singular. You can put all the singular monopoles together on a point. You still have a large moduli space whose dimension is half of the dimension of the Poisson variety. Which is I guess you could call it the invariant locus of the C star action, right? If you think of
I don't think it's invariant locus of C star action. I think it would be the attractor of the fixed point by A, not by the loop rotation, but by A, because A has like
I want the
exactly
loop. It's the loop rotation is the interesting thing, not so for example, okay, let's do the very simplest example, okay? The very, very simplest example, the stupidest example you could do is just C2. That's an example of a Grassmannian, right? Where we take what do we take? We take SU2 we take one spin, one spin and a half insertion, right? And you lower the weight by 1. Okay, so that's C2. It's just C2. It's nothing else, right? And then the thing that scales the holomorphic symplectic form is just dx dy, right? And the thing that's invariant under scaling is product of x times y is equal to 0. Okay, so that's 2 lines. That's x is equal to 0 union y is equal to 0. So in that example, right, my monopoles, I have one monopole that's moving on a real line, right? There's one singular monopole at the origin, and it gets complexified by one variable. So that's my fixed locus. That's what the thing I call core of x.
I think we're talking about different spaces, to be honest.
Oh no, no.
No, just I would think about the C2 as you explain it. I would think about I have action of 2-dimensional torus, right? Like one scales one coordinate axis and the other scales the other coordinate axis. And the thing which preserves symplectic form would be like one thing I scale by t,
exactly.
the other I scale by t inverse.
That's right.
And the one which doesn't preserve would be tt. So it scales everything together.
Sure.
So the loop rotation, which destroys the symplectic form, would have the only fixed point, the origin.
That's right. But there's an invariant locus is bigger. It's the product of both lines.
It's not the invariant locus if I include loop rotation.
So.
And it's not even invariant under. It's invariant, but it's not fixed. Right? Because the points here move, even with respect to like the second torus.
So
maybe what you're thinking about is like invariant subspaces. Then surely like it has bigger thing. But I'm talking only about the fixed
So I think that's why I was saying this is a terminology question. I think I know. You in this example you mean the fixed point is just the thing that's truly fixed is just 1 point. That's right. That's true.
Okay. Good.
Good.
Yes. Sorry that it caused some confusion, but
it's okay.
Yeah. Okay. So and this is a singular space, but it's Poisson variety, and we can ask when it admits a smooth resolution which is symplectic. Almost like this. So when it admits a symplectic resolution, that's a slightly more technical thing than this. So and in this case, we know it is known when this has a symplectic resolution. My favorite reference here is Kamnitzer-Webster-Wikis-Jacobi. Maybe, I'm not sure, maybe it was known before that, but that's the first reference I found. The earliest reference I found. So for this, we know that if lambda is a sum of minuscule co-weights, and remember that minuscule co-weights correspond to something smooth, then we can actually construct something called convolution Grassmannian. It depends on the order of lambda, unfortunately. Depends on order.
I think this was known to Kapustin and Witten, for sure.
Possibly.
I'm sure it was known to people like Zhu or the guys from Langlands.
Yeah. So we have this, and it's constructed as it sits in L copies of Grassmannian. And you can think about it as I record what happens after I do Hackett transformations. So I start with trivial thing, then I make it into something monopoly here, and I record what transformation I actually make, and so on. So this is always the same. And then if I record only the last thing, that would be something sitting in this Grassmannian lambda mu. So altogether transformation is actually the point. But I should actually look how it's stacked from elementary monopoles. So sometimes they cancel. That's why actually my total charge here is mu, not for some points it's mu, for something it's between something mu and lambda. But I tried to allow it to be as big as lambda. Okay, and this is smooth, symplectic. And actually here, symplectic form is a T eigenvector, and it has weight h bar. That's the weight which corresponds to this C star H. That's why I called it like this. Okay, and this map is proper, birational. So that's why I think of it as a resolution of it. Moreover, my T action is actually the same. It can be lifted, T equivariant. And symplectic structure on the smooth part is the same. So I resolved the singularities in such a way that I can actually extend the symplectic form, and it turns out that here you can do everything without destroying the T action, which is great because we can still do T equivariant localization. And we see that actually this space has as many parameters as we have in Knizhnik-Zamolodchikov equation, right? So let's discuss the examples we have here. So my favorite thing is to consider examples in the plane where on one line I do the dimension of the torus, which is the number of equivariant parameters, and the other is the dimension of Picard tensor with. So if I take out all the torsion, what would be the dimension of Picard? That's how many Keller parameters I have. So Keller on the vertical thing and equivariant on the other thing. So first of all, if I act only by one-dimensional torus, but I want to increase the Keller, the number of Keller parameters, that would be, here I can take the resolutions of plane modulo the so that's a singularity of type AN, and you can construct its resolution. The exceptional divisor is known to have a certain number of components, and they give you the generator of Picard. Okay, the other thing is if I keep only one Keller parameter and I allow my torus to be bigger, here I can take T star of G mod P, where P is maximal parabolic. So that's minimal parabolic corresponding to minuscule weight. Minuscule co-weight. So all usual Grassmannians will be here, or as a special case, PNs. So they are also here. And one more good family. I'm not claiming that all things on this line are of this form, but that's the most notable things which you can study by other means. And on the diagonal, where you have the equal number of scalar and equivariant parameters, would be the cotangent bundle of full flag varieties. So they're also here. And these guys are all smooth for the resolution of AN singularity. That's already formulated like resolution of something affine. So you have this construction. For all the others, you just take affinization, which is the Springer resolution. So just you take only all global functions on this thing.
In the language of the Affine Grassmannians, what's T star G mod B? Like, which weights would you have to choose to get T star G mod B?
Oh, sorry, this is in type
This
A.
is not, it's in type A, it's only, okay.
Yeah, right. Yeah, thank you for correction. But in type A, you should just pick n copies of the fundamental. Yeah, sorry. I should have said it. Okay, so now if we allow this resolution, we will actually have more fixed points. That's
actually remind me. It's a tangent. I hope you'll allow. T star G mod B. What's the quantum differential equation of that in general? Is it known what it is? I thought that Andre must have worked out.
Yeah, so it was known, I think, for Braverman, Molik, and
that's right,
exactly. In there. Yeah, so I don't think that they definitely computed the quantum multiplication there, but I'm not sure if they stated clearly what the.
I think they did. Okay, never mind. Okay.
Yeah, sorry.
I just wondered if you remember.
No, I'm sorry, I don't remember this one.
It's a tangent, so I apologize.
Okay, so so when we do the resolution, surely because this is T equivariant thing, all the fixed points would be in the preimage of mu. And it turns out that there will be finitely many of them. Okay. So the T and A fixed loci are the same for this resolutions. And actually, they have a nice interpretation in terms of, so you can write it explicitly. As I said, a point here is an L tuple. So it would be just a collection of points with some, oh, sorry, I called them Z. That will be L points where sigma I are co-weights. Increments here are in the Weyl orbit of lambda I, which is the same as saying that R weights in the representations of Langland's dual group, right, with this highest weight. And the last condition, so here I actually used these parameters that the increments are not higher than lambda. And one more condition which I have comes from altogether thing being contractible to mu. It actually says that the last one is actually mu. So that's a way to construct mu from increments. And I can actually think about this. They can be drawn as paths from 0 to mu. So I start from mu, from 0, and then I go by some reflection of lambda 1. Then I go by some reflection of lambda 2. They could go back and forth, but by the end of the day, I have to arrive to mu. So lambda i's are, if you want, lengths of the segment, not actually, but almost. And then altogether, they should add up to mu. This is how you think about it in 2 dimensions. Surely, if you live in A1 type, you would more likely think about it as just spins up and down, which will be still this picture, but I can go like this.
This has as many terms as the dimension of the space?
It has as many terms as my L, which is how many minuscule co-weights I have.
Oh, how many minuscule co-weights you have. Okay, I didn't understand this. Let's try this again.
So I have L tuple, which is how many minuscule co-weights it is, how many Hecke modifications I allow. And each Hecke sorry, Mina, you
remind me, what are you explaining? What is this path? I guess I didn't understand that.
Oh, that's the fixed loci of the resolution.
I thought the number of fixed points is the dimension of the weight space.
Yes, it's the dimension of the weight space, because you see here the condition on increment is that it's sum of the weights of the weight space. And then they all together should add up to mu. So yes, right, this is in bijection. With a basis in. I'm just saying how to look about it, like from the language of, from the definition of the spaces. So. So if you wanted each step, you allow just Hecke modification, which is like more or less t times the increment, sorry, z times the increment. And this increment is a weight of the next thing. Yeah. And we see that actually here we need the order. It's okay. So this thing actually will show us how that at least the spaces can be related. But precise way to relate them will be just choosing basis in both of them. Okay, let me go back to this a little bit later. One more ingredient which I need in my identification is line bundles, equivariant line bundles. So, and here, there are some line bundles. So as I said, my this guy lives in a product, L-fold product of the Grassmannian, right? So this gives L projection maps. Just project to a certain copy, right? And then I could do the following. I know my favorite line bundles on the Grassmannian, which are O's. So just take line bundle Li, the pullback of O1. These are not quite the ones which I want, because I want the ones which behave like EIs in AN root system. So I will use the other ones. These are Li divided by its precessor. That's an increment in line bundles. Okay, and these behave more like E's in behave like EIs in N root. In A, I think it's a L minus 1 here, root system. Okay. In particular, for example, if I take the Chern character of all of them and sum them, then it would be 0. Right? That would be the same as saying that this is 0, the usual case. Okay.
How many such line bundles do you get?
I get all of them, but sometimes they are not truly independent. So sometimes there are more conditions on them. In type, so for a generic difference between lambda and mu in type A, for example, that's always just this. There are no relations. But for example, if I take lambda equals mu, let's do a stupid example. Lambda equals mu, that's just a point. Then all these line bundles, even though they're defined somehow complex in a complex way, would be just the same line bundle. So they are possibly some relations between them.
These things should have like tilting line bundles. So there should be basically a set of as many line bundles as the dimension of equivariant cohomology or equivariant K-theory.
Oh, but you can construct tilting from these ones. So you can also take their powers. So for example, if you consider T star of Pn, you will have one line bundle, but the tilting generator would be O plus O1 plus so on. So there will be powers of this.
Yeah, I guess, right, okay.
In terms of equivariant Picard, they are related. Okay. So that's why I focus on these ones. So they span the equivariant Chern characters span the second cohomology. Mm-hmm. Non-equivariant. So like if I add just like scalars, that will generate the equivariant one. So if I add trivial ones with different weights. So that gives me the base. So this more or less will be my ith direction. Okay. And because in Knizhnik-Zamolodchikov equation, we have actually z's which behave in like AN root system. And they only enter in terms of their difference, so they behave like roots in AN system. That would be more or less this. Okay, so these are the line bundles I actually want to consider. And in terms of these fixed points, you can write very explicit formulas about their restrictions, compute all degrees of them with respect to curves you like. So they're very easy to work with. Okay. So that's an explicit definition of directions in my space. Okay, and now what basis do we take? So localization says that if I take equivariant cohomologies and I take the restriction map to the fixed locus, as it is, it's not an isomorphism. But if I allow to invert certain characters, certain elements of the cohomologies of the point, then this becomes an isomorphism. So where M loc means M tensor over cohomologies of the point, which is just the functions on the Lie algebra, polynomial functions of the algebra of the torus, with a fraction field or the same thing. In other words, I just allow to divide by whatever characters I want. So then this becomes an isomorphism. And this is just a vector space over this fraction field of dimension number of points in xt, because they're independent. So I can work with it as just usual vector space. Okay. And this map is given just by pull back along the inclusion. Or in other way, it's restriction, right? And this gives at least two bases. One of them is just, okay, if it's an isomorphism, let's invert it. And let's take some bases in here. So I can take just one at one particular point and zeros everywhere else. So that would be bases here, and then I just we'll see where it goes here. And unfortunately here it's bases only after localization. So these are non-localized classes. Sorry, these are only localized classes. So if I try to do any computation of them, unfortunately, I always can get a rational function. And for rational functions, it's very hard to, they can be very different. So there's very little control over computation. Little control. Sorry. Okay, another thing I can get is push forward of the class. This is better. This is a non-est class, but the side effect is that degree of it is high. So this is non-localized. This can make sense without localization. But it belongs in the twice the dimension of x. Which is actually high. And if you'll try to do anything which involves pairing between two such elements, you will have a polynomial of degree the dimension of x. And that's also hard to control. You have too many terms. Okay. Actually, there is a way, there is a basis which lives in half the dimension of this. It becomes basis only after localization, but these classes are non-localized. And these are Molikov and Okunkov. Stable envelopes. They also depend on a point, and they live in the dimension. So they are better classes in some sense. Oh, for many purposes, but mine is just most ground to earth. Just they have sufficiently small degree that the dimension axiom here gives significant restrictions on what I can get. In most cases, I can make sure that everything I'm interested in is just a rational number, not a polynomial. Okay, so from technical point of view, that's how you, that's why you're interested in them. And fortunately or unfortunately, they have an extra parameter. They have the chamber. Okay. Should I review some properties of this envelopes, or we can just take it as a black box?
You can say a couple of words just to give people a feel for how to think about it.
So, okay, so one way to think about this thing is that's a refined version of the Poincare dual class to the attractor to P. And surely the notion of attractor depends on the chamber you choose. So that's some sort of corrected version of the attractor. That's why it takes half of the dimension, because we live in the symplectic world. So for any attraction direction, there is a repellent direction. So that's why you get a half. If I look at the restrictions, the restriction matrix, then this is triangular. With respect to attraction order. Okay, one more thing is that off diagonal terms are 0 modulo h bar. They are divisible by h if that's off diagonal. Right. And maybe the last nice property I want is that if I take stable envelopes with respect to the opposite chamber, this is the dual basis to stable envelopes with respect to the ordinary chamber. Okay. So that's why they become very useful, because when you want to compute coefficients with respect to stable envelopes, you just take tensor product, or if you just take pairing with stable envelopes, but of different type. Okay. Okay, so we can discuss two things here. We can discuss the computation of the classical part, which is non-trivial in if I use the basis of stable envelopes. It has this asymmetry. It gives you the half of the Casimir. And the other thing is the purely quantum multiplication. So what should we do? What do you prefer to discuss?
Maybe tell us about the classical part.
The classical part, okay. Okay, so we want to compute the classical multiplication this. Okay, and because we want to express it in terms of other stable envelopes, we will actually consider, as I stated before, we'll pair it with the dual basis. And here I assume that D is a divisor, so it lives in second equivariant cohomology. Okay. Then by dimension count, so each stable envelope has degree dimension of x, and then 2 comes from the divisor, and then I should subtract twice the dimension of x when I take the pairing. So altogether, that would give me that this lives in second cohomology of a point. right? And actually, that means that it's just a linear combination of weights of A and H, possibly, H bar. Okay? And if, sorry. If P is not Q, then this is divisible by H bar. So it's actually some rational number times H bar. If P is Q, then we have prescribed values for stable envelopes on the diagonal. And this is a straightforward computation. So the only thing you need to know for both cases maybe about the diagonal case, I'm oversimplifying. You still need to know the data which I'm writing now, but okay. Yeah. The only data you know, the only you need is the restriction of stable envelopes modulo H squared. So only the first possible correction. And this is relatively easy to find. Okay. So you know that the part which doesn't depend on H is only on the diagonal, and the part which depends linearly on H will be found during this thing. So the first step would be to find this formula in A1 type. So first find this in A1 type. And there it's easy because there are explicit recursive relation. So they actually work not even modulo H squared. They are just you can compute all the stable envelopes there easily by some recursion, which comes from action by correspondences, by Steinberg correspondences. Okay, and the second thing is that for G of general type, just look at the following thing. If stable envelope of P restricted to Q is not zero, has a possibility to be non-zero, then it implies that stable envelope with respect to the minus chamber is zero if the points are distinct, right? If one is lesser than the other, then if I change the order to completely the opposite, I'll have zero by triangularity, right? And then you can say that now I start with this chamber minus C, and here I know the value. And if I change my chamber when you cross the wall, you can control what happens to the stable envelope if you know x fixed by some character sigma inside of x. And sigma should be this, should be the character on the wall, generic character on the wall.
Which kind of walls are we talking about here?
In equivariant parameters. So they are separated. I'm changing the equivariant chamber, which is in the stable envelope in its definition. Okay, and this turns out to be, this is slice of type A1. And because you know what happens in type A1, then you can do it. It's not true that you can do it if you don't require modulo h squared. There would be some corrections which are which take into account how some interplay between different components of this variety. But if you stay only in the first non-vanishing order, actually everything happens only in these components. They don't talk to each other. So each time you cross a wall, you have some very explicit formula. And that gives you the computation. Okay, so each of them would, so these walls are actually, walls are roots, right? So that gives you the summation over all roots. And for each particular root, I will get a contribution which is EF, because in type A, type A1, the restriction is not 0 modulo h bar if P and Q are related by F tensor E. So if I think about them as, well, that's a path in one dimension, but let me draw it in 2 dimensions. So this would be the number of my step. And here I will just take the parent between where I am at step 1. So this is keeping track of position, and this is which Hecke modification I actually made. So that would be some sort of something like this, and then it ends at mu paired with alpha. Okay, and what I mean by they are related by EF, it means that somewhere here I lowered, then I kept all the increments the same, and then somewhere here I raised it. So this would be like action of F, and this is like action of E. So it gives me terms of type FE, and only in this order. That's why I have half of the Casimir in classical thing. So that's more or less where it comes from. And for type A1, that's a direct computation. Recursive relation tell me what happens if what happens to stable envelope if I remove one box. So I can think about this as partitions, right? So if I lower exactly one corner or remove one box, I know what happens to the stable envelope. And then I see that just modulo h bar that gives me that only these things contribute, and I know exactly their coefficients. So that's more, then you have some work like actually keeping track of all the numbers, but these are numbers, there's no polynomials, they're much easier. And then you need to match them to what you see in Knizhnik-Zamolodchikov, but they do match. and they do match both in ADE and BC types. So this part actually is the same. What is different is the when I try to curve count. Unfortunately.
Yeah, right. No, I think the thing to do in B and C types, you have to do something slightly funny. As you need to work equivariantly with respect to rotation of the curve itself. So more precisely, your space should be such that as you go once around your curve, you permute the nodes by an involution of the Dinkin diagram. That's how you should be getting non-simple lace cases. Otherwise, so if you just study the affine Grassmannian of a non-simply laced G, it's not going to work, right? You get some.
Yeah, that's what I see.
Right.
So I just maybe so what I see, I have for long roots, I have some curves, but they have for long roots they have twice the degree. That's why instead of like power series in terms of z, I have power series in terms of z squared.
Right.
So maybe in what you tell, I would be able to have like half of the curves.
Right.
And then possibly it is the case. I agree with you.
Right. Yeah. No, I did some. Yeah, I think this is needed to even get the equivariant ordinary classical K theory correct, I think. Otherwise, nothing really matches. So I did some simple calculations like of Holmes between sheaves, and that this makes sense. Like you know, I needed, for example, to understand what are the vanishing cycles that you need for knots. And if you do what I said, then it works out. And if you don't, it doesn't. And this is also what string theory tells you should be doing. And then there's some slightly more. There should be yet another way of realizing non-simple lace theories, but it's a little. That's a little bit. You should add an additional discrete equivariance, which rotates the disk in the affine Grassmannian. That's a little less geometric. I understand this one a little bit less well, but I think it should actually also make sense. That was my conclusion at the end. I haven't thought about this in a while because I think, but we should talk about this in maybe a couple of weeks.
Okay. And by correct K theory, what do you mean? Just what are you trying to match it?
So what you're trying to well, there should be some non-simple lace theory that well, whose Knizhnik-Zamolodchikov equation would be the Knizhnik-Zamolodchikov equation of the Langlands dual of non-simply laced affine Lie algebra, right? And what you're looking for is well, we're trying to compute the unknot, right? And so what's an unknot? An unknot is a home between two halves of a knot. Between a sheaf that's two halves of a knot, right? And that and what Simon's invariant of an unknot computes is just the Euler character of the home, and it's a simple calculation. It's just but you see that this involution where as you go around the circle, when you're defining the Euler characteristic itself, that's the same circle that that's rotating your curve. That the way to get the correct Euler character is that as you go, you work in a simpler lace theory, but as you go around the circle, you have some permutation of weights that by this involution. I can show you the calculation. It's not. So it's some kind of twisted equivariant K theory that works out, and that should be that sort of tells you what you're doing at infinity of your of the disks that of course whose solutions are generates.
I see.
Whose equivariant Gromov-Witten counts are generating solutions to your equation.
Okay, got it.
Right.
Thank you. Yeah, I think then I'll stop here.
Okay.
Just yeah. we still have purely quantum part, but yeah, I think
this is understanding the classical ones is the interesting part. The quantum one somehow goes along for the ride. I think.
Yeah, just as long as you introduce the steps, it's just pretty straightforward. They're just designed to work there, and like it doesn't much differ from the argument like Braverman and Malik and Danilenko had like long before. Like, yeah, but it's surprising that like in classical case you have wall crossing in equivariant parameters. Then in purely quantum part, you have wall crossing in terms of Keller parameters to compute them. And then magically they give you the same answer. Like altogether it combines into something.
So let me ask you this. So good. The stable envelopes, what do they look like in, you know, we talked about this that you can think of. If you think of, you know, T star P1 hypertorically, it's just a line, you know, with 2 points on it, right? So you can also have that kind of picture of an affine Grassmannian as well, right? Yeah. It's just a symmetric product of points on a line with some insertions. Are we okay with that?
Yeah. Yes,
this is just the locus in the fixed locus in the monopole moduli space of, sorry, the invariant locus in the monopole moduli space of your C star action.
Yes, but
are we good with?
Yeah, but
I just want to make
I don't think there is an easy answer because like
no I'm asking. I didn't actually ask the question yet.
No, yeah, sorry. Okay.
So stable envelopes are some holomorphic Lagrangians. These Affine Grassmannian being what it is, there's a lot of representation theory there. So I know somehow using Neurosymmetry how to construct the tilting line bundles on the Affine Grassmannian, and which are like which are in some sense like projective representations, and how also to construct the dual simples. But then you can ask, okay, so what are all the other gadgets? In particular, what in that world are the stable envelopes? So the question is, what do they look like in this basis? Do they run along the line, or they're half lines? I think they're half lines. They're half lines. Of course, they're half lines. Even for C2, they're half lines.
They go to one direction.
One side or the other, yeah.
But the thing is, if you try to like what you're doing, actually, you're trying to categorify everything. So from what I understand, stable envelopes on categorical level, they are Fermat modules.
Yeah, that's right. That's right.
So yeah, when you say what category O, you actually chose some preferred direction there. So and that's the same direction you choose in stable envelopes. So they're infinite, but they're infinite in one
way or the other, yeah.
Yeah, right. And surely they're somehow like between the projective and the simple.
Yeah, right. That's right.
So in this setting, yeah, they appear to be something like this.
Right.
So at the moment, we're trying to actually understand what's the categorification. We're trying to do it with Andrei Smirnov and Vasya Krylov. So yeah, they are Fermat modules, but we are not sure like
I think
what the generality we can do it.
For example, Neurosymmetry is extremely powerful there. It's very for example, to show that you have a tilting line bundle is one line calculation. Just the very existence of a tilting line bundle is a one line calculation. That such things exist, and you know you can characterize them specifically. There's I mean, you know, in half a page you discover, like, you know, generalizations of Bondal's results on exceptional collections, like on P1 to you know, to these kinds of spaces. So it's very, very beautiful, and there's obviously representation theory all over the place. And just this like simple thing of just like understanding what are my symbols and so forth.
That's actually very interesting for me because before that, the only way how I knew that a tilting generator exists is this Kaledin-Bezrukavnikov working with.
No, this is
quantization and
extremely easy.
Morphy.
So for them, they
So-
had trouble understanding, you know, for example, just what is this H bar equivariant action? Here, this is an easy calculation. It is astonishing how simple it is. You can actually you can compute the whole algebra. It's just, it is. I'm still amazed just how simple it is. It's literally the easiest calculations you've ever seen done. You know, mirror is completely, that kind of calculation is completely classical, as it should be, as soon as you're doing anything with tilting generator. And it's calculable.
That's actually very surprising for me. Just
yeah,
I was trying to do something like this, but without like this background. So yeah, for me it was hard. That's very interesting that on your side it's.
Yeah. So for example, you know, this is this Webster paper on quantization of Coulomb branches.
Yeah.
This. So I haven't worked out all the ADE types, but I've worked out SU2 completely, and it takes, I don't know, an hour. It's just, I mean, it's easy, and you can actually, you know, I can give you the whole algebra with generators, like everything you ever wanted to know, the structure constants, everything. It's amazing.
That's interesting.
Yeah, so it's a beautiful story. These are beautiful spaces, amazing, actually. So, okay, thank you very much. And
thank you.
We should talk about these non-simply laced things at some point. So, yeah. Okay. Thank you.
Okay. Thank you.